Okay, let's start. Hello, my friends of Qatari Labs. Welcome to this webinar. This webinar is to determine the missing crop vegetation areas. So when you have places where you are supposedly going to have a vegetation, and then you don't have, whether that the plant is missing or like the foliar area is also missing as well. Okay, if you hear me well and if you have the files downloaded and placed, okay, so for this webinar, what you are required to do, okay, so here you have this link, so you can place this in another browser, for example here. I can place it here and then it will look for a password. So this is Hatari Labs with capital H. Okay, and then you download the files. It's actually okay. Okay, so we have downloaded the file and the downloaded file is here, Control C, and then we place this under documents. Okay, everybody please place this under documents, and then here we are going to extract here. Okay, so you should have this under your document folder. If you have this under your document folder, please type 1. If you have this under your document folder, please type 1. If you have this, please type 1. Okay, great. So we are going to type anaconda prom, okay, and then here we are going to see the documents, see the webinar, okay, and then here we launch Jupyter Lab. Great, so here we launch Jupyter Lab. If you are here with me, please type 2. If you are here with me, please type 2. If you are here with me, please type 2. If the Jupyter Lab, if you have your Jupyter Lab where you have the data, and on the data you have a raster, okay, and that is the orthophoto, and then you have a shapefile that this shapefile is the area of interest, okay. So if you have this, please type 1. 2, 2, 2. Please type 2. If you have any problem, let me know. If you have any problem, let me know. Just my friend Ali is the one that is here. If you have any problem, let me know what we can do for you. Who else? Yes, Ali. Setting Ayman Abudaye. Okay, well, great, Ali. Okay, so here we are going to use a new notebook, okay, and this is going to call webinar. Great. So this is going to be called webinar. Okay. So what we are going to do here is that we are going to work with a class that actually recognize the orientation of the rows, okay? Even that we, on the missing crop parts, we are not going to exactly determine how many plants are missing, okay? What we are mostly interested is into, well, but this tool actually exists, so it will be very handy for you. So I say from working functions, import crop recognition, import geopandas as GPD. Okay, Chief Enter. Okay, so we have imported the geopandas, and there are some depredation issues. Okay, but we are not going to pay more attention. Okay, Ali, if you are here with me, please type 3. If anybody is here with me, please type 3. Okay, if you are here, great, 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 great. Okay, great. So we are going to use and instantiate our class. Crop lines is equal to crop recognition of the data raster, and this is the well, this was taken from the data set of open from drone mapper. Okay, so here we have the crop lines. Okay, and this is my suggestion. When you have a lot of tools or something related to where you have done a lot of code, okay, and then you want to reproduce it, it's faster to do it on, it's really, it's faster to do it on a Python class, okay, instead of just type doing code one by one, okay. So this is crop lines is equal to dot band. Okay, so we are in order to do the crop recognition, we have to select one band. So that is why we select the green band. So this is number 1. Okay. There is a question here that say, could you repeat how to start Jupyter Notebook? Okay, just go here to the document and type Jupyter Lab. CD documents, CD webinar, okay, and Jupyter Lab. Right. So, so we can do the crop lines dot plot band. So we can plot the band, and this is okay. So this is the band. Okay. So we see some missing vegetation here. Okay. However, you can use 500 because you can, okay, we can plot a specific part of the band. Okay, great. So these are the plants and these are the shadows. Okay, we are going to fix the shadows with a filter. Okay, and then we see here some missing vegetation. Okay, if you are here with me, please type 4. So we are going to crop lines is dot, we are going to fix the band. Okay, and why we are going to fix the band? Because there are shadows. Okay, so we are going to do okay, if you go to the Python, we are doing some filtering. So on the shadows we are going to put, okay, for the shadows we are going to put a value that is close to that, and this is what this method does. Okay, so and then we can plot crop lines dot plot band. Okay, so we can 500 times 500. Okay. Okay, now this band fixing is actually, it's going to take some time because I think that this looking for each value, I guess. Okay, let's wait till it's finished. We are going to get rid, okay, why we fix band? Because we are going to get rid of the shadows, okay, because the shadows are not vegetation, okay. And if you want to recognize, if you really want to recognize the alineation, okay, so, and I will tell you that the code will look for the orientation of the shadows, okay, not the orientation on the, not the orientation of the crops, okay. So let's see working functions. Mhm. Okay, let's wait. Mhm. I think that it got stuck. Did it finish for you? Please type 5. Okay, I will stop this, and I think that okay, I can kernel, I can restart my kernel, restart. Mhm. Something has happened. Okay, I don't know what has happened. Okay, something has happened maybe because I'm launching so many things. Okay, if this happens, okay, I'm just going to launch Jupyter Lab. Okay, so you are not supposed to have this, okay, to encounter this, since sometimes it happens to me, since I'm doing the streaming, and since I'm doing the streaming and running this, so it is, sometimes it has happened. Okay, so I'm going to restart. Okay, so I run this, run this, run this, run this, and then the next one that it was crop lines fix band, crop lines dot plot band 500 times 500. Okay, let's see that. Let's hope. Okay, great. So it has, okay, what it has worked is with the shadows. So actually the shadows and the barland or the grass is on the same and the same color. Okay, great. Great. So we are going to define the threshold of the candy filter. Okay. So what does it mean? So wait, just to type. Okay. So the candy filter actually delineates the, okay, in order to recognize the alineation, you need, okay, in order to recognize the alineation, what you need is to somehow filter the borders of the vegetation. So for that, what we are going to do is crop lines dot cani min crop lines dot cani min. Okay, so we define the threshold of the cani filter. Okay, cani max, and in this case, and this will depend on your this will really depend on your crop, okay, because for some crops you will have higher thresholds, okay, or lower thresholds. Well, it cannot be lower than that, but okay, so and then we can plot our canny filters. Crop lines is equal to canny filter display grade. Okay, now it's doing the canny filter, okay, and it's showing for the canny filter 1, 2, and 3. And this is amazing. Okay, please look at this. Okay, so it shows the canny filter 1, the 2, and the 3. And from candy filter 3, actually you start losing detection. Okay, so actually doesn't detect. Candy filter 2 is working great. Okay, if you are here with me, please type 4, 5, 5. Great. So you are maybe okay. So we are going to define the sigma of the candy filter. So say from the analysis crop lines dot cani sigma is equal to 2. Okay, so and we define the okay, and the cani filter is a this is a boolean. Okay, so whether it's vegetation or whether it's not whether it's border of vegetation or whether it's not border of vegetation. Okay, so and this is a boolean array. If you okay, I have tried with one. Okay, and the problem is that it detects many rows. Okay, so actually doesn't detect only one row, but it detects many rows. Okay, but you can try with one, don't worry. So that is why with two actually detects only one row. And for some places it even detects one. Display hog transform. Mhm. Okay, so we are going to display the transform the crop lines. Mhm. Okay, so this is the input image, this is the Hawks transform, and these are the interpreted. Okay, for Sigma 1, actually, this is even more. Okay, so there are more lines, interpreted lines. Okay, if you are here with me, please type 6. Mhm. Okay, so we open the area of interest is equal to gpd dot read file of data of shapefile of area of interest. Okay, so we are going to crop lines. So because the analysis will be only on this area of interest according to this Python class, okay, to this method. And this is kind of practical because I mean sometimes you have raster files that has some empty areas, so actually you don't want to do analysis on an empty area, or you have ways or highway, not highways, you have some access ways in your crop field, so you don't want to do this on those crop on those areas. Okay, I log 0 geometry, so we okay, so crop lines dot aoh. Okay, so this is the area of interest. Okay, and then we create the lines in the area of interest. Okay, so I say crop lines dot lines to AOI. Okay, so we are going to crop to the extension of the AOI. Mhm. Okay, so it's cropping the lines to the extension of the AOI because actually you are not. Okay, so it has finished. If you are here with me, please type 7. Okay, and then here crop lines dot create shapefile of data. Okay, and then this will be called crop rows. Okay, so because what you are interested is in what you are interested here is in defining the crop rows. Okay, so we are going to create a shapefile. Well, this shows you some the minimum, the max, and the average and the median. Okay, and this is the shapefile that is has been created. Okay, this is the shapefile of the alienation. Okay, so and then we are going to plot our raster with the alienation. So say import rasterio, import matplotlib mat. Setting has pro. I can if that isn't okay. Yeah, this is an error of your proc 4 and this can be related to your installation. Actually, I'm not this, maybe you have to look for that. Okay, but if you were able to run the code, but if it's an error, you weren't able to do that. Um, what I can suggest you is that after this webinar, you reinstall your Anaconda because maybe it's because you have some older version. From rasterio dot plot import show df is equal to gpd dot read file data crop rows, okay, the one that we have created. Image is equal to rasterio dot open of data raster orthophoto cliff. Mhm. Okay, great setting. Okay, so this is AX is equal to AX. Raster show image of AX equal to AX alpha is equal to 0.8. Build.show. Okay, so we run this. And then under this, okay, so we see a great fit here. Okay, and why we see a great fit? Because actually we got rid of the shadows. Okay, because There was a tutorial before that what was interpreted was the shadows, and under this we have, for example, this problem of two lines. Okay, so and this is because we are on Cani Sigma 2, maybe with Cani Sigma 3 or 2.5 that can be different. Okay, but I leave that to you. Okay, if you are here with me, please type 8. Mhm. Okay, great. So now we are going to work with the missing path. Uh, yeah, you can do a method that understand, not that do not work exactly with the Canny filter, but like it works with the distance among lines. Okay, well, I leave you like that because I mean the when you have too close lines, okay, so one do not have to exist. Okay, so you can do a filter in between that if you have a line that is at the same distance of the other won't appear, something like that. Okay, so now we are going to work with the missing plan. So image is equal to rasterio.open of data of raster of ortho. Okay, so let's see the CRS to EPSG. Okay, so to EPSG. Okay, so we are working with data on this system, right? Mhm. Great. So now we are going to now what we are going to do is that we are also get rid of the shadows, okay? But in this case, we are going to do it manually, okay? So for that, we have the RGB as a dictionary. For the band 1 will be the value 159, for the band 2 it will be the value 118, and then from where you get those values from QAS, because you actually look for the minimum value that you allow, and then by picking on the on with the pixel evaluation. Okay, so these are the values that come from here. So in red band is equal to image read 1. Okay, that is great. And for the red band of red band less than the full RBH of the for the value of the red band, it will be okay. So what we say that all the values that are less than this will be replaced by this value. Okay, and this is in order to get rid of the shadows. Okay, and then from this we do the same for green band. Green band, where green band is less than 2, this will be 2, and this is for the blue band, this is 2 as well, and this is 3, and blue one, where blue band is less than 3, is 3. Okay, great. If you are here with me, please type 9. What is the what is your question? Which is your question? Yeah, sure. Mm-hmm. Mm-hmm. Mm. No, because actually the ones that are smaller than for example 100 or there are shadows. Okay, if you go to because that is okay, you have to open the raster in QAS and then you have to inspect the pixels and then from those is that inspection you will get this threshold. Okay, okay, setting. Okay, yeah. Mhm. So we do okay, and then we do a Hatari index. Okay, Hatari index is okay. You can do it without Hatari index, but actually it works. Okay, so we use red band. I mean the fixed red band plus blue band. Okay, divided by green band. Okay, so and then plt dot imshow of Hatari index of 500. 500. Okay, so and this is the view. Okay, so we can do that as well with just one band, but in this case with the Hatari index we got something better because actually the missing, okay, so this is the normal vegetation. Okay, this is the normal vegetation. This is the empty rows and the non-vegetated part or the partially vegetated parts appears really clearly, okay, on the color map. Okay, if you are here with me, please type 1. If you are here with me, please type 1. Okay, great. So now what we are going to do is we are going to define the contour. Okay, we are going to find contours about this. Contours is equal to, okay, so we have to import the some package. So from Scikit image import measure, import numpy SMP, import Fiona. Okay, great. So contours is equal to measure. We are going to find the contour. Measure dot find contours of Hatari index of 0.5 contour and this is contours. This is contours of 0 of the okay, just to show you the contour, but this is our contours over the array. Okay, this is contours over the array. uh, okay, great. uh, why? Because we have to turn these contours into geospatial coordinates. Okay, if you are here with me, please type 2. Okay, great. Let's continue. Okay, now we are going to sample the list. Why? Because you are going to get contours, okay? But as long as the missing part is bigger, okay, you will have more vertex, okay? So we have to sample how many vertex has each contour. So that is why we use sample list. Mhm. Okay, for contour in contours, sample list, append contour dot shape 0. Okay, so we can, okay, so with that we have a list of all the vertex from a contour. Okay, sample list. Okay, so for example, here we have that the first item has 77 vertex, while the second only has 3, and the second only has 3 maybe it's just a small dot, so it's actually not of our interest. So we want to have a quantile of the, for example, just to, in order to define a threshold with a better approach, okay? So we have sample list, so we have the quantile 90 of this, so how many vertex is the quantile 90 of this sample list is 31 vertex, okay? If you are here with me, please type 3. Any questions, let me know. No, we are not going to plot, we are going to filter. Whatever has less than 31 vertex, it will be omitted, okay? And then we are going to evaluate that through the results, okay? Great. So now are going to pig ax is equal to plt dot subplots of fig size 12,12 ax im show Atari index alpha is equal to 0.5 contour list. Okay, so we create a contour list. So I say for contour, for contour in contours, if contour shape 0 higher than the quantile or higher than 31, but in order to put it here, generic is sample list or 0.99. Okay. Okay, we can do that interactively. Okay, explode contour, okay, of the y vertex. Ew. Yeah, because yeah, no, the x vertex and the y vertex contour line width is equal to 2 contour list dot append contour x dot set x lim 0 to 500 ax dot set y lim is 0 to 500. Okay, plt dot show. Okay, let's see. Actually, it's taking some time for me. Okay, does it finish for you? Please type 4. It has finished for you. Please type 4. Okay, so here we see, okay, the parts that are empty and where the contour actually appears. Okay, so say, okay, this part is empty, okay, and then you have a polygon. This part is empty, okay, you have a polygon, and so, okay, that is great. So we have defined the empty parts, I mean the parts that that are supposed to have vegetation, but it doesn't. Okay, if you are here with me, please type 4. Who else? Okay, great. And now we have to define our contours. We have to export it as we have to export that as a shapefile because we need that as a shapefile. Okay, so that is why we are going to use Fiona geometry is typed by polygon properties id int. Okay, so this is okay. And now we are going to work with Fiona. Okay, so let's say poly shapefile is equal to fiona.open, and this is data slash missing vegetation dot shapefile. The mode is equal to w, and the driver is equal to srich shapefile. Okay, it has to be srich shapefile how I have written. Okay, otherwise it won't work. Schema is equal to schema, and the CRS is equal to image CRS dot to string. Okay, great. For index contour in enumerate contour list xy list is equal to C. For vertex in contour xy is equal to image.xy of vertex 0, vertex 1. Okay, so now we generate a list dot. Okay, so we have to do a conversion because the contours are in row column. Okay, so we have to convert it to XY. Okay, so XY. Mhm. Row dict is equal to this is pure Fiona. So mhm. And then we poly shape write. We write the dict poly shape dot close. Okay, great. So with that, we generate our shapefile. Okay, and it's already generated. Okay, if you are here with me, please type 5. If you are here with me, please type 5. Mhm. Who else? Mhm. Great. So now we are going to do some recycling. So what it means about the recycling is that we are going to use these 3 lines. Okay, we are going to copy this because we want to plot. Okay, so the first one is df1 is crop rows, df1 is crop rows, df2 is missing vegetation, the image is the image. Okay, so far. Okay, and this is the line show is df1, and the other is the poly show. Poly show is df2, uh, and this is color royal blue. Mhm. And this is color crimson. ls is equal to dashed. Okay, great. And then we can plot our image. Great. Uh, df1. Ah, okay, okay. This map is actually not going to. Okay, great. So if you are here with me, And then we can define, okay, so if you want to do some ax.setXlim. Okay, and then here you see the results and are quite impressive. Okay, here alpha is equal to 0.5. Why they are quite impressive? Because we were able to recognize the rows and as well the parts that do not have vegetation. Okay, and this part of do not have vegetation can go for an analysis of your fertilization or whatever it takes. Okay. Okay, so setting, could you say that? Yeah, yeah, yeah. Mm-hmm, mm-hmm. Yeah, because this is just as a limited part. Okay, if you are here with me, please type 6. Who else? Okay, so that will be the this webinar. Thank you.